This took 40 days of gradual pumping to achieve, during which time the tubes were heated to over 150 degrees Celsius to expel as much gas as possible from the metal surfaces. Just getting the tubes ready for that evacuation took immense care. Establishing delicate equipment in remote areas of the United States was not without its problems. The tubes are big enough and took long enough to construct for the local wildlife to take up residence. When a member of the team walked through the near-completed tubes at Livingston, he discovered that wasps, black widow spiders, mice, and snakes had all moved in, and that meant acid-bearing urine, leaving stains on the pristine stainless steel that would release vapor when the air was removed, requiring a major cleaning effort before that vacuum could be established. That word stainless in stainless steel doesn't apply once acids are involved. Despite the intense vacuum within the operational tubes, their metal walls are just 3 millimeters thick, around the same as 50 sheets of standard A4 paper. Without the frequent reinforcing loops along the length of the tubes, the outside air pressure would crush them. The exterior of each tube is cased in concrete, not to resist the vacuum, but to cushion any outside impact. This is just as well as a security truck collided with one of the tubes of the Hanford Observatory at night. The driver suffered a broken arm, but the tube stayed intact. A damaged tube, allowing air at atmospheric pressure to pour in, would have been catastrophic. The resulting blast of air would have destroyed most of the detection system, causing many millions of dollars worth of damage. Because the arms extend for such a distance, their supports have to gradually increase in height along their length to cope with the curvature of the Earth. From one end to the other, there is more than a meter difference in height needed to keep the tube perfectly straight. And this was just a small consideration in ensuring that the detectors can function properly. A far bigger issue was vibration. To deal with the inevitable environmental vibrations, LIGO has a whole host of feedback systems, which monitor position and make tiny movements of the arms and components to compensate for changes. Positions are monitored 983,000 times a minute, once every 0.000061 seconds. The seismic isolation platforms deal with the larger vibrations, down to around 1 million times larger than the waves that LIGO has to detect. The remaining reduction is achieved by the remarkable suspension systems used to keep LIGO's mirrors from moving due to anything other than gravitational waves. These use 4 separate pendulum suspensions to dampen movement, dangling the mirrors from glass fibers just twice the thickness of a human hair, keeping the 40-kilogram test mass mirrors as stable as possible. Business as usual. During the engineering run in September 2015, all of LIGO's detection systems were in play, bringing the light beams into alignment and testing their functionality with no thought of capturing a breakthrough observation of a gravitational wave. For over 50 years, scientists had been looking for the tiny distortions in space and time caused by a distant cosmic event that would add a new, powerful approach to the astronomer's armory. They had never achieved a single result. Some even suggested that gravitational waves would be impossible to detect unless we could take the leap of building an observatory in space, as the tiniest local tremor was enough to confuse the incredibly delicate instruments. But for now, these worries were put to one side. No careers were at risk of yet another failed detection of these elusive waves on this run. It was simply a matter of ensuring that the technology behaved as it should. However, just because this was an engineering run did not mean that the observatory was inactive. Unlike the dome of a traditional telescope, with shutters to prevent light coming in, there is nothing that can stop gravity.